Can you record the class?
Oh, I guess Emmanuel started recording it.
Yes, yes. Thank you very much, sir.
Okay, okay. Then. So, like I said, Adobe 2 is more or less an upgrade from Adobe 1. So, those major failures and setbacks that were suffered by Adobe 1, it was worked upon and improved in Adobe 2. So, Adobe is more or less like an open source project where anyone, you guys, me, or anyone in the world, anywhere in the world can contribute to. So if you feel there is a major problem and you find a way of tackling it, so you can reach out to the GitHub, to the Apache team GitHub and work on improving Hadoop. Yeah. So whatever your solution is, when you try to push it to the repository, some repository administrators will go through it, and if they're okay with it, it will be added to, yeah, it will be added as an upgrade to the next version of Hadoop. So that's how open source project is more or less like. It gives room for anybody to be able to work on it and improve on it. So that's why we have Hadoop 2 now. Okay. So the major objectives of today's classes, we will try to list the various components of the Hadoop 2 ecosystem. Then we'll discuss the process of storing files in Hadoop distributed file system. Then we'll explain the roles of Hadoop MapReduce and Yarn, explain the roles of some other major Hadoop applications and other tools and resources used in interacting with the Hadoop ecosystem. Okay, I guess we have the last person in class now. So moving on, here we are, the Hadoop ecosystem. So yeah, in your last class, when you were introduced to different technologies for handling big data, like I'm sure you've been taught about in-memory usage, distributed computing, parallel computing, and all other stuff. Yeah, and they would have also taught you about Hadoop. Then they would have taught you about cloud, using cloud tools and the rest like that. Does anyone who knows the engineer that built Hadoop? Were you guys told? The software engineer that built Hadoop. Does anyone here knows the name of the engineer that built Hadoop? Okay. I would assume no one knows then. So Hadoop was built by a software engineer from Yahoo. His name is Doug Cotton. So I'm going to type his name in chat section, just in case if you feel like having that as an extra knowledge. So that was the young man that built Hadoop that everyone, almost every big data enterprise or company makes use of software today. Okay, so going on, Hadoop was developed because it represented the most practical way to allow companies to manage and process huge volumes of data. So I'm sure you've been taught about batch processing, how Hadoop helps to lift the heavy weight of loading every data or real life data that is being streamed, then separating it into different chunks to be fed into different servers. Okay. So generally, you have different components of Hadoop, but the major core components of Hadoop is you have three major core components of Hadoop. So you have the HDFS, which is the Hadoop distributed file system. You have the MapReduce. Then there's also a software layer of the Hadoop ecosystem, which is the Yarn. Yet another, which is the Yarn. Yeah. And yarn means yet another response navigator. Yeah. So, like I said, from my screen, you should be able to see there are so many components of the Hadoop ecosystem. You have the HDFS, you have the MapReduce, you have the YARN, you have the HBase, you have the Hive, you have the Pig, you have the Scoop, you have the Zookeeper, you have the Flume, you have the Uzi. So to make it simple for you guys, I would say, so generally, the major three components, yeah, of the Hadoop ecosystem normally is the HDFS. HDFS means Hadoop distributed file system, the MapReduce, and the software layer, which is the YARN. While the remaining, which is the HBase, the Hive, the Pig, the Scoop, the Zookeeper, Flume, and Uzi, they are all different applications or technologies built on the Hadoop ecosystem used to interact with the Hadoop ecosystem. So they are more or less like, so I know from Pig, Scoop, Zookeeper, and Flume, and Uzi, they are mainly softwares used to interact. They are mainly applications used to interact with the Hadoop ecosystem. Like now, some of these softwares basically, okay, so this is how it is. If I'm to classify it in another way for you guys, so um, for those that are not really so into, that don't have a technical background, that don't like coding, for non-developers, so they're able to relate to the Hadoop ecosystem better using Pig and Zookeeper. For those who love coding, they relate to the Hadoop ecosystem using HBase, Hive. If you are talking of HBase, you are talking of programming in Java. You are talking of Hive, you are talking of programming in SQL. Then Scoop, basically from the name, you know that Scoop means it was formed from the combination of two names, which is SQL and Hadoop. So if you pick the first two letters in SQL, you have your SQ. Then if you pick the last three letters in Hadoop, you have your OOP. So that's how Scoop was formed. I'll be explaining each of them as time goes on. Okay, so this is more or less like a diagram explaining the different tools and technologies in the Hadoop ecosystem and commercial distributions like that. So funnily enough, I would say this diagram actually, this is not everything that you can use to relate to the in the Hadoop ecosystem. So it's far more than this. Like there are even so many softwares, so many applications that might not be mentioned in the class, but it's based on whatever the operation you're trying to carry out is. So basically, if you need to do something, then you have to find out, oh, which application or which Hadoop tool or technology can I use to carry out this. So that's just how it is. So, okay. So I'm going to talk about HDFS now. So what is HDFS? HDFS, which is an acronym for Hadoop Distributed File System, is a data service that offers a unique set of capabilities needed when data volumes and velocities are high. Okay. And what else? Okay, I guess it's already summarizing. It's like HDFS allows users to write to file only once at a time at the time of creation, then avoids coherence issues that might result from replication of data. Then one thing I need you guys to know is HDFS is not the final destination for files. So HDFS basically is more or less like a file system for the Hadoop ecosystem. So how would if I'm to give it a real life example, I would want to say you should look at it like more or less like your file explorer or Windows Explorer. Yeah. Just see it as something like that, that houses all other components. So, okay, the major function of HDFS is it is a useful, tough and clustered approach of storing and managing very large amounts of data. It can be in gigabytes, terabytes of files. So, in your normal file explorer or Windows Explorer, you can have all sorts of files that have different memory sizes. So just see it like as if you use it to store different data, different blocks of data. That's just like from the name implies, Hadoop distributed file systems. It's basically used for storing different blocks of data, different blocks of files, and the rest. Okay, so I would be going to the HDFS architecture. So, like I said, I don't know how many of us have heard of data centers before.
I have.
Okay,
I have
so
also.
I'm sure if you've seen different movies, like for those that have seen series like Mr. Robot and the likes. So if you notice, Jerry, the company the Mr. Robot guy works with, they have different data centers. So imagine you have a data center like this. So this, what you can see here is more or less like a cluster. This is the cluster in the data center. So you can have so many big machines like this connected together, distributed together by different pipelines in the data center. So if you drill down in for the HDFS architecture, you have this is a cluster, so you have different servers. Each rack is more or less like a server. So for the normal Hadoop one ecosystem, in one rack of server, you have the name node, you have the data node. So as you can see, definitely the data node is what stores or what holds the information, what holds the data. Then the other racks, you have the different data nodes. You have different data nodes. So if you notice from here, you have a major server that carries the name node, that carries the data node. What is the name node? The name node is more or less like a master server for storing different metadata about for storing different metadata for storing metadata about the data you are housing in the data node. So what do I mean by metadata? So metadata is more or less like description of data you are storing. Yes, it's more or less like having a log of data that you are storing. I'm trying to use simple terms here, but I don't know if you guys are able to get what I'm saying here. Okay. So what does the name node do? So the name node keeps track of where data is physically stored in the data node. Like I told you, it stores the metadata, everything about the data, where the data stays in the data node, the location, the directory, everything about the data. The name node does that. Then the HDFS cluster maintains file system namespace and controls the file access for clients. So it's just like your normal File Explorer or Windows Explorer operations. You are able to navigate around the HDFS like as if it's a normal File Explorer going from one location to another. So it stores different folders in different places. That's what they mean by namespace actually. So the name node keeps track of where data is physically stored in the data node. So what does data node do? So data node performs the file read and write operations in addition to block creation, deletion, and replication once the instructions received from name node. So you can see name node as the master that it gives instructions to the data node on what to do with the data. Okay, the name node also carries the information how data should be distributed across the different servers, across the different data nodes on different servers. So name node is more or less like you can see it like as the administrator in the HDFS architecture cluster. Okay, so yeah, as you can see from this slide I have up here on my screen. So reading it, it says the blocks are stored on data nodes and it is the responsibility of the name node to know what blocks on which data nodes make up the complete file. Just like I said, blocks here refers to data or information. They are stored on the data node and it says it is the responsibility of the name node to know which data or which blocks are stored on the data node. So meaning, let's say I have data concerning Okay, let's say I have data concerning different cities in Nigeria now. So if on the first server, if on this first server, this first commodity server, I store all the cities in the southwest region, then on this second server, I store all the cities in the south, I store all the cities in the northeast, like that. So it is the duty of the name node to know where each file or where each different bucket that I've saved, where each different data block is saved on the different data nodes. So it is the responsibility of the name node to keep track of information like that. So name node is critical for correct operation of the cluster. Hence, it is replicated to guard against single point failure. Okay. Let me take that again. Name node is critical for the correct operation of the cluster. Hence, it is replicated to guard against single point failure. So what does single point failure mean? So single point failure means, okay, so look at this now. In this architecture you have here, you can basically just see one name node inside this Hadoop cluster. But one thing you need to know is there's another name node on standby. So what does this mean? It means if this one fails, it switches to the standby one. So single point of failure means you're having just one appearance of just one item. So how would I explain single point of failure? Single point of failure means, let's say you have just this name node and this data node in this cluster, and you don't have these other two servers anymore. So that's a single point of failure. It means if this data node should fail or should crash, there's no other data node to work with in this cluster. That's what single point of failure means. It means not having extra replicas of that entity or that block you are trying to work with. That's what single point of failure means. So your Hadoop distributed file system, like I said, it works by breaking large files into smaller pieces called blocks. So that smaller pieces called blocks, you can refer to it as your data. So it also says the name node also acts as a traffic cop, managing all access to files, including reading, writing, creating. I already told you name node is more or less like the administrator that is coordinating most of the operations of the data node and the HDFS system. So data nodes constantly interact with the name node. So it's more or less like a master and worker relationship. Definitely, if name node is the administrator, data node should be able to communicate with the name node. So any data node that is unable to communicate with the name node picks it up and is notified of the availability of that data node. So the name node is able to track which data node is not working at any point in time. So it would be able to pass out the instruction of should they switch to a standby data node on that server, which is on that rack or not. Okay, so going deep down, data node provides heartbeat messages to detect and ensure connectivity between the name node and the data node. So they're just trying to explain to us how data nodes communicate with name nodes. So data nodes are able to communicate with name nodes with a form of messaging referred to as the heartbeats. Yeah, heartbeat messages. So if you look at this diagram here, on your master rack, which is your master server, you have the name node, you have the data node. You notice this name node is communicating with this data node. Then on another rack, you have this data node. They are not showing any name node there. You have this data node, you have this data node. If you notice, this one here communicates with the name node, as you can see with the arrows. This name node communicates with this data node, but this data node doesn't communicate with this name node. As you can see, it says no heartbeat, meaning there is no communication. So that's how the name node is able to detect if a data node is working or not through heartbeat messages. So features of the Hadoop distributed file system. When files are broken into blocks and then distributed across different servers in the cluster, any variation in the operation could produce incorrect data. HDFS uses the following features, blah, blah. So the very first thing about HDFS is transaction logs. Like I said, it keeps track of every single thing, every single operation you run in the Hadoop cluster. Then checksum validation. It verifies which contents of files in the HDFS. So what do I mean by checksum validation? So imagine you are trying to query a data warehouse now. So the HDFS work in a certain type of way. Okay, it communicates in a way whereby, okay, let me say I try to query the HDFS. I say, okay, give me a list of items from a database named cities. So I've queried, give me a list of items from database named cities. So there is a numerical computer value that is attached to that query. So normally expect that, okay, that's more or less like a select query. That's more or less like a list query. So there is a numerical value. Let's say the numerical value is, let's say it is 10 now. So by the time the HDFS computes this operation, okay, by the time the HDFS computes this operation from the different clusters, then sums it up. If it is not up to 10, that operation is not going to run. That's what we mean by checksum validation. So there is an expected value that is required for operations to run successfully in the HDFS. That's what we refer to as checksum validation. If you don't get that, I can still take it one more time. So, okay, let me know if you don't get that. Then data blocks. So what does that mean? It ensures the failure of one server may not necessarily corrupt a file by data blocks replicated across several data nodes. Then data pipeline supports movement of data across the servers. Okay. So functions of the data block: stores and retrieves the data blocks in the local file system of the server, stores the metadata of a block in the local file system of the server, sends regular reports. So, okay, let me go back to this. So this data node now, it carries, okay, yeah, this is even the best way. So this data node now, you can see this diagram. It's more or less like 3 disks attached to each other. So let's assume that each disk is a data block, like that. So if one fails, the others will keep working. That's more or less, that's how a data node is. So there are some on standby also that you wouldn't necessarily see in the diagram. So what do these data blocks do? These data blocks, they store metadata about data in the local file system. They perform periodic validations of file checksum, just like what I told you. If the result of a query is meant to give me a certain value, it will check out if that value is correct. And if it is not correct, the operation is not going to run. Then it sends regular reports to the name nodes about available blocks. Like just like throughout bit messaging, it's lets the name node to understand to know which data blocks or which data nodes are not working. Then it supports direct access from different client operations, meaning you can access the HDFS distribution system through different clients application, just like your Scoop, your Zookeeper, your Flume, and your Uzi. Then it forwards data to other data nodes through based on pipeline model, and that's based on instruction provided by the name node administrator. Okay. So your HDFS manages block of files by performing the following step. So your HDFS keeps one replica of every block locally. Then it places a second replica on. So this is what I explained earlier as regards single point of failure. So the HDFS works in a certain type of way whereby you can say it's more or less like elastic. So it has a clone for almost every block or rack in the data center. So going back to this diagram now. So for this particular master server now, this particular rack in the data center in this cluster now, it has a replica of this particular one. So in case this one fails, it just loads the replica automatically. So that way it has been able to evade the problem of single point of failure. So meaning there are clones of different servers of different blocks available to work at any time, though this consumes more space in the cluster. Then it sends the third replica to the same remote rack, but to a different server in the rack. So this whole process is just basically explaining how the HDFS creates multiple clones of itself, trying to replicate itself in the data in the Hadoop cluster. Then the HDFS also has another operation that is referred to as federation. Okay, so the name node has the name node has in memory a reference to every file and block system in file. Yet on every large cluster, memory may become limited and amper scaling. Okay. So it's still basically the same process of cloning itself. For every entity in the Hadoop cluster, you create an extra replica or you create a block somewhere in the server so that in case it fails, you load it. So you can see, okay, so since the name node has in memory a reference to every file and block in the file system on every large cluster, memory may become limited and unpasking, just like what I said. You know, when I told you in the last slide that for every block or every rack in the data cluster, for every rack or every block in data cluster, it creates an extra replica of it, like it creates clones of it. That way it's eating up memory. So how does Hadoop 2 tackle this? So what it does is that the failure of one name node does not affect the availability of other namespaces managed by other name nodes. So meaning it creates additional name nodes on different clusters or different servers elsewhere in the data center so that data nodes register with each name node in the cluster and stop blocks from multiple block pools. So it's more or less the same process of cloning yourself for every entity that is in the data architect in the HDFS architecture. So for this now, there is a clone. So this just it in simple terms. Forget all the old big that I'm trying to put together. This is just it. For the name node, it has a replica somewhere. It has a clone somewhere. At least one or two clones somewhere. For this data node on this commodity server, it has two replicas in different places, be it locally or somewhere else on another server. So for this data node here, you can't say any name node here, but the information about this data node is also stored on another name node somewhere on another server that isn't shown in this diagram. Then this data node also. So it creates more replicas. It creates more of itself in different locations so that in case anything happens to all these entities here, there wouldn't be any crash of operation or failure like that. It can always revert back to the other entities on standby carrying the same information. Okay, so that will be all for now. Just give me 5 minutes, please. You can put your questions in the chat section or just raise up hand if you have a question. Okay, let me know if you have questions. Let me know if you have questions while we are still taking some time to quiet. And I hope someone is preparing to answer this question on my screen here. Okay. So what is the function of data nodes and name nodes in the Hadoop distributed file system? Can someone help us with that?
Okay. To simply put it, data nodes are where your data are stored, where data is stored. Then, while the name node is like the administrator, it replicates all the data. It stores metadata for the data that is stored in the data nodes. It generally functions as where you can read, check, validate, and all that for the data node for data nodes. That's what the name nodes does, and the name node is being replicated just in case for any single point failure.
Okay, thank you so much. Yeah, I also want to hear from another person. I guess that was Daniel, right?
Yes, sir. That was Daniel.
Okay, so someone else. I'm expecting someone else to talk. Should I call anybody's name? Okay, Richard. What do you have to say about data nodes and name nodes?
Okay, so data node and node node, they work like the master and slave relationship. Node node is the master, while data node is like the slave. So data node stores actual data in the system and also send information back to the node node. So I didn't really get to explain, but that's what people got from the lecture.
Okay, thank you very much. That's awesome. So you guys did well. Okay, so we have another question here. Wow. What does a block server do? What does a block server do? Who's going to answer this to us? Should I call someone's name also? What does a block server do? I'm sure people are already getting confused, but I'll just go back to it again. So this is everything. This is everything a block server does. It stores and receives the data blocks in the local file system of the server, stores the metadata of the block in the local file system, sends regular reports to name nodes about available blocks, supports direct access to data nodes. Okay. The block server refers to the server that stores data in a file system and metadata of it. So for people that don't know what block server is, look at this. This is one block server here. It carries a name node and a data node, just in case you didn't know what I was referring to as data block or block server. So that was what I was also referring to as the racks also that you plug into this system.
Is that a question, sir?
Okay.
Um, Looking at the definition or the function of a data node, is there any similarity between block server and data node? Looking at data node stores data also, and looking at what they say about block server refers to a server that stores data also. Is there any similarity between them or something?
Yeah, you just said this. They both store data, but I'm going to explain this to you now. See, so your block server carries entities that store information. So your block server is also storing information about the data nodes and the name nodes. So if you check this, if you notice, because your block server carries information about the name node and data node, it is able to detect which of these blocks is free for memory allocation or data allocation. So if you check from the functions of the data block, it stores and receives data, and it stores and retrieves the data blocks in the local file system of the server, stores the metadata of a block in the local file system, performs periodic validation of the checksum, still regular reports of the name nodes about available blocks, supports direct access to the data nodes. So it's more or less like storing information about the entities itself that do the real work, forwards data to other data nodes based on pipeline modeling. I don't know who asked that question. Were you able to get what I'm saying? So the data node is and the name nodes are more or less like it's the block server that carries them, the data block that carries them. So that's why the data block is able to get information about different name nodes and different data nodes. Then it feeds everything to the central name node, letting the major name node know which data blocks are available for data allocation or free of memory so they can be used. I don't know if I've been able to answer your question.
Yeah. Thank you very much.
Okay, so you said there is a delay in the movement of my screen. Okay, I'm going to try to share my screen again. Can you all see my screen now?
No,
Okay, sir.
no, I can't.
So who cannot see my screen? Um. Okay.
If I can see it now.
If you can't see my screen, please let me know. Data, I think something's wrong with your network. Cause I can barely. I think I couldn't get what you said. Hello, can you all see my screen now? If you can't see my screen, please indicate before I move on further.
Not yet, sir. I can't see your screen.
Okay, you can't see my screen. I'll try resharing. How about now? Can you see my screen? Can you see my screen now?
No, we can't. We can't see your screen. I can't see your screen. Sorry.
No, that's
Wow. If you can see now, can you type yes in chat section, please? Can you see it now?
No, sir.
No, we can't. We can't.
No,
I
sir.
can't see your screen, sir.
Ah,
I can't see your screen.
Oh. How about now? Let me know if you can. Because I've shared my screen like 3 times now. I've shared and shared again. Emmanuel, can you confirm if you can see my screen?
So, Emiola, I
Yeah,
don't think I can see your screen.
you can see my screen too.
Yeah. Wait, what are you sharing actually? What are you sharing?
Guy, I've shared the Chrome tab and I've also shared my entire screen. I'm currently sharing my entire screen right now.
Okay, try and go to maybe another page so you know. So what are you showing at the moment now?
I'm showing you guys the slide.
Okay. I can see your screen now.
I see my screen now.
Yes, but it's taking time to come up.
Let me know when you can see my screen. Though.
I can see your screen.
So should I say it's people's network or what?
I can see your screen, sir.
Okay, that's good.
Can see it
That's
too.
okay. So the second major component of the Hadoop ecosystem that we'll be looking at is the map reduce. So um, the map reduce is as the name implies, it was gotten from the map reduce algorithm. So basically, I want you guys to see MapReduce as an engine because that's exactly how it works. You provide file to it, then it converts that file, then outputs whatever you inputted into it, processes it, then gives you the answer you need. So MapReduce is a framework that uses in processing large amount of data stored on different systems. MapReduce simplifies parallel data processing and is known for its popular implementation in Hadoop. So Hadoop MapReduce, it includes several stages, each with an important set of operations to get different answers for big data problems. Okay, all right. Okay. Okay, so MapReduce is an implementation of the MapReduce algorithm, just as I told you. So MapReduce is a tool that helps business organizations to help handle both structured and semi-structured sources of data, which are not easy to analyze with traditional tools. So basically, when you were doing introduction to big data, they would have probably taught you about the different formats of data, which is the structured, semi-structured, and unstructured format of data. Okay, let me ask a question from that. The emails, the data gotten from emails, chats, and the rest, which format of data or which structure of data can we classify them as? Your emails or your WhatsApp chat or or WhatsApp messages from a group chat? Which structure does it belong to? Is it structured, unstructured, semi-structured? I'm going to ask which Yeah. How can we which class does it belong to? Does it belong to structured, semi-structured, or unstructured? Is it we terminal on this call? Hello. Okay, since the terminal, Hubert, which structure of data does emails and chats from WhatsApp group chats belong to? Is Hubert also not on this call? Okay, it be terminal as answered. It's unstructured ideally. So basically, data that comes in forms of chunks of text, of characters, we can refer to them as unstructured data. So basically, those are data we use as raw input for modeling operations like your natural language processing and all. But in a way, sometimes those unstructured data they can come in semi-structured format. Like now, your messages from any WhatsApp group chat or from your WhatsApp API. If you are going to getting it out in raw format, you would have a column for the time the message came in. You have another column for the name, then another column for the WhatsApp message itself. So in that format, it's actually semi-structured. But if it comes at, let's say, a JSON file that is just a collection of different characters in different rows, then it's unstructured that way. Okay, so your map reduce basically.
Hello, sir.
Uh,
Okay, sorry. Before you go further, I might have a question, and I won't want us to go too far before I draw you back. Going back to the HGFS architecture, I'm sorry, I'm drawing us back. We mentioned the name node and the data node. So I would like to know, in a standard HGFS architecture, like how many name nodes do we have? Is it just one, or we could have several? Or when we go to the data node too, is there a standard number of data node that we ought to have, or we could just, I don't know if my question is clear.
So, very good question. Thank you very much. So you could the data the number is not defined. It depends on a lot of things. Number one, it depends on the kind of operations, and number two, it depends on the memory allocation you have for each block or for each commodity server or data block you have in that HDFS architecture. So it's not predefined. It just depends on a lot of things. Like I said now, if you exhaust your name node now, you can have, it depends on the kind of operations you are basically doing on it, because the name node needs to replicate itself, the data node needs to replicate itself, and from what we've learned today, it can have up to 2 or more replications. So it depends totally.
Okay.
You can't have a predefined number.
Oh, okay, sir. Thank you.
Okay, so MapReduce. So MapReduce, it consists of two primary processes that programmers build: map and reduce. These programs runs in parallel on a set of worker nodes. MapReduce works in the following manner. A MapReduce worker processes the data received from the master and sends the results back to the master. Each MapReduce worker runs the same code against the portion of data. So how would I say it? You can say MapReduce is more or less like saying you're talking of the engine that runs the process that was explained in, let's say, your your parallel computing here, because if I can remember well, the person who would have taught you guys about parallel computing or distributed computing would have told you that for parallel computing is like you are given a certain task. Let's say I'm making a select statement now. The select statement is my task. So that task, the scheduler or the map produced master takes that task, then shares it into different processes. And in Hadoop ecosystem, since our data is already separated into different data nodes, different data blocks, so it will run that task, that my select statement task, on different data nodes. Then it will give me the result of that my task, that my select statement on each data node. Then when it gives me the result for data node 1, it goes to the next data block or commodity server, gives me the result. Then it aggregates it and sums it up together to me the final result. So just like what it says here, the master then integrates the results received from different workers and does the final processing of the data to get the final result. So it's more or less like it is the engine that runs your batch processing or parallel computing in your Hadoop ecosystem. So that's what MapReduce does. So it maps out the tasks into different processes to different portions of the data. Then it sums it up together, it sums the results, then it sums the different results, then reduce all the different results together by aggregating it to a single final result. So that's where the MapReduce, that's what MapReduce does. It is that engine that does your parallel computing in the Hadoop ecosystem. That's just a simple way of understanding it. So let me use this flow diagram to explain it now. So let's say I have 20 terabytes of data and 20 MapReduce server nodes. So it distributes a terabyte to each of the 20 nodes using a simple file copy process. Just like I said, it distributes that your data, maybe that your select statement task, into different server nodes. Then the program submits 2 programs to the scheduler. One is the map, the other is the reduce. So what does the map does? The map program finds the data on the disks and find the data on the disks independently on each of the different servers. The result of the map steps are then passed to the reduce process to summarize and aggregate the final answer. So just like the name implies, map reduce. So I've given a task now. For that task to run, it maps out that task to different servers, different commodity servers. So the response gotten from those different commodity servers, it then reduces it to a final aggregated response, which is the final response I get for running that task. So let's say, just like I told you about cities in Nigeria now. So let's say in my first commodity server, I have cities in the south, the second one I have cities in the southwest, like that. So it will run down my select statement on the different portions of the data. Then after doing that, it will then reduce the responses gotten from the different portions of the data to a final response that justifies my select statement. So meaning right from that's where even your checksum validation even comes in. Right from the point of me making that select statement, that particular task, there is a certain value that is expected as a return value, but you are not aware of this in background. You are not aware of this as you are programming or in background. So if my select statement is even wrong in the first place, it will return a different value. So that means that operation won't be able to run. But if the select statement and the syntax and everything is correct, it will be able to run properly. Then it gives me a result. Okay, so what are the strengths of MapReduce? MapReduce can handle some issues better than a relational database. So like I told you, relational databases, they have their flaws in handling of unstructured and semi-structured data. But with MapReduce, you can even analyze and gain business insights from real-time data that is streaming at a very high velocity. Maybe you're talking of tweets coming from a Twitter account, from different Twitter accounts now, from a particular trend. with MapReduce, you can just pass all the old different tweets as a chunk into the Hadoop ecosystem, then run your MapReduce tags on it to get a certain insight on it. Meaning, with MapReduce, you are querying unstructured and semi-structured data directly without even having to be a headache of maybe cleaning it or reloading it into an REDBMS or so. As you can see, say short stacks include things like passing of text, crunching through web logs, and reading a huge raw data set, a raw data source. Okay, I already said all this. MapReduce can sort data irrespective of the data size and extract the important part. So MapReduce is, so you can also use MapReduce. Is also used like an extract, load, and transform tool on many occasions. So meaning you can use MapReduce for your ETL processes. Okay, let me explain that to someone that doesn't know now. So let's say normally the text or the raw data gotten from, maybe I want to run sentiment analysis now on people's review of a certain product now, and I've gotten the different chunks of their ratings and their reviews and everything. So with MapReduce, I can just pass it in straight and just use ManOut to run a machine learning modeling operation on it. And straight up, I'm able to get sentiment analysis, those ones that were being biased, those ones that were being that gave unfair reviews to it, those ones that gave promotional reviews to it, or probably maybe they just wanted to just lie about it. So I can run all sorts of sentiment analysis directly. But if I'm to load that raw data for the sentiment analysis into a normal RDBMS or normal flat file like a CSV fast file, now I have to use my stop words to remove unnecessary words that I don't need, like DA, which is normal NLP operations. I have to use the count vector vectorizer to turn those words into different bags of words, to class them into different chunks of word, creating a column for each word that appears in the sentiment analysis. So all those processing and everything, you would have to do it normally if you had to, let's say, load it into an RDBMS or a flat file. But MapReduce does all of that for you automatically, meaning you don't have to bear the headache of removing stop words. You don't have to bear the headache of bagging your words into different buckets. So all of that is done for you by MapReduce. So what's the weakness of MapReduce? MapReduce is not, like I said, MapReduce is an engine. It is not a database. So it lacks security. You cannot index query. You cannot do process optimization, and you cannot get historical perspective in terms of other jobs executed. You can't have access to them. Knowledge of other existing data, you can't have access to them. Then MapReduce considers every job as an entity in itself. It is not aware of other processes that may be running simultaneously. Then another issue with MapReduce, a major issue with MapReduce is, with MapReduce, you have to define your data types, meaning MapReduce comes with the responsibility of having to define exactly what type of data is created in every process, meaning you have to be aware of your data structures. Everything is more or less going to be custom coded, meaning with MapReduce, you'll be doing a lot of coding, like I said, including data structures. Then MapReduce is a relatively new concept. Not so many people know how to use it or code it or use it well. And again, one thing that I've noticed is people don't like to get involved with things that involves a lot of coding, a lot of hands-on experience, especially when it comes to writing high-end codes or scripts. So now we are going to go to the software layer of the Hadoop ecosystem, which is the yarn. Remember what I said, that for the Hadoop ecosystem, you have three major components normally. Normally, you have three major components. You have the HDFS, which is the Hadoop distributed file system. You have the MapReduce. Then you have the yarn, which is yet another resource negotiator. Okay. So you have the yarn, which is the yet another resource negotiator. So the yarn is the software layer of your Hadoop component. It provides two major services. It provides two major, sorry, okay. It provides two major services. So it provides global resource management, then it provides application master, that's per application management. So I want to see it this way. Most of the hardware components and application, you have the HDFS, you have the map reduce, then the software layer, which we basically use more or less as for load balancing operations, is the yarn, which is the software part of it. So I'm going to explain in details now. Okay. So the yarn, just going to read out the slide. It contains detailed CPU, disk, network, and other important resource attributes necessary for running applications on the node and in the end cluster. Each node has a node manager, saved to the global resource manager in the cluster. Okay, so I want to explain this way now. I don't want to call the every manager scheduler, manager scheduler, manager scheduler. So I'm going to take us back to a certain diagram, because I notice if I do the normal way of explaining it, will most likely be lost, because I'll be calling a lot of managers like the node manager, the resource manager. So if you notice from this diagram here, like I said, you notice from this diagram here, the name node is more or less like the master that monitors everything. Then the data node are like the slaves, according to what Richard said. So the name node gives out instructions on which data do you store on the data node. Then the name node also stores information about the different data stored on the data node. So the name node is more or less like the administrator to the data node. But in the Hadoop ecosystem, so the administrator, what you can refer to that performs administrative operations in the Hadoop ecosystem, when you have the map reduce, you have the HDFS, is the yarn. So the yarn is more or less like the software layer that you use for your administrative operations for for resource management and for application management, meaning which resource or which application gets to use the certain number of cores, get to use this number of threads for its processes. So it's more or less in charge of the administrative process for the different operations of the map reduce, the HDFS system, and the rest. So the yarn contains what you know as the resource manager. The resource manager is a master service and control node manager in each of the nodes of your Hadoop cluster. All the required system information is stored in a resource container. So like I said, if you are the admin, you have information about the different things you are having administrative roles over. So the resource manager will definitely have the yarn with effect of its resource manager would have information about the different name nodes, data nodes, and the node manager like that. So it's the node manager that does the name node administrative operations. So it will have all the information about it also. So just it like as if you're having an administrative set of roles over some things. So definitely you would monitor the processes, you would have information about those processes, you'll be able to assign which resources are used by different processes, different applications running in the Hadoop ecosystem. So I want to see the node manager monitors the application usage of CPU, disk network, and reports it to the resource manager. So it's the resource manager that does the, let's say, global resource management in the yarn. Then another thing you need to know is, we said yarn performs two major services: global resource management and per application management. So the global resource management, what performs that operation is the resource manager, and that resource manager works hand in hand with the node manager that acts in the name node, and the name node performs administrative duties over the data node. So let me take it again. Yarn performs global resource management. It performs global resource management with the help of a certain resource, of a certain tool known as the resource manager. The resource manager communicates with the node manager. This node manager is coming from the name node. It is what does the exact administrative functions of reporting, monitoring, distribution of processes and nodes in the name node, giving instructions to different data nodes. Then you also have, for application management, the yarn does this with the application master. Wow. So with the application master. So the node manager negotiates with the resource manager. That the resource manager, like I told you, is the one that determines which resources are used, the scheduler, and the rest like that. So the node manager is also responsible. So yeah, we can just see different functions of the resource manager that works in the yarn, the node manager that works in the name node, which gives administrative instructions to the different data node and passes instructions via different data blocks to other name nodes and data nodes in them. Then the application master, what does that do? So basically, what that does is, what the application master does is that if, let's say, more resources are needed to run an application, the application master communicates this to the resource manager in here. So the application master and the resource manager, they are both the two main entities that speak to one another in the yarn, which is the software layer of the Hadoop ecosystem. So what the application master does is just monitoring of resources needed to execute or run different applications. So if it sees that, okay, it needs more resources to run a certain application, what it does is it communicates with the resource manager. So it's like everything in the Hadoop ecosystem is reporting to a central governor is like they are submitting different budget and invoices requesting for resources from a central governor, which works from the yarn known as the resource manager. Okay. Please, okay, your hand is up. Do you have a question?
Sorry, I was going to ask you to help me put down the tab that is hanging, the floating tab on your screen. Like I wasn't seeing the details here again, so but I've not been able to get my hand as well.
You said what? I can't really hear you. Maybe we need to reduce volume of what's making noise there.
I said you might have to, like, I wanted to ask you to remove the floating tab on your screen so that I will see the details that was on the screen then. But I've not been able to drop my hand down, so that's why it's been a while now.
Okay.
So I wanted to ask if you can just minimize it entirely, that black floating screen. Okay, thank you. I think it's fine now. It's hanging up.
Okay. So now let's go to, actually we still have time. Let's go to storing data, big data with HBase. So HBase is more or less like, how would I put it? It's more or less like an application you use to interact with the Hadoop ecosystem. So basically, the programming language you use with the HBase is the Java programming language. Then what else? So HBase has similarity to your RDBMS, but it is not entirely the same. So what I mean by RDBMS is your relational database management system. Okay. HBase is a columnar database. It enables all data to be stored in tables with rows and columns, similar to that of RDBS. Okay. the intersection of a row and column in HBase is called a cell. Then HBase has the function of version tracking, which you don't have in your normal RDBS. So versioning tracks changes in the cell and makes it possible to retrieve any version of content if necessary. So at points of intersection, maybe where at different points whereby you are streaming your data, HBase attach timestamp to them for you to be able to get any data format or any data set at that particular timestamp. So that's where versioning comes in, being able to get data at a particular timestamp in HBase. So for HBase, the map is indexed by a row key, column key, and a timestamp, just like I explained. Each value in the map is an uninterrupted array of bytes, okay? So like I said, is a major difference between HBase and your RDBMS is versioning. Your RDBMS, your relational database management system, does not have versioning, but your HBase has versioning attributes, just like I told you. So HBase are highly scalable, they are sparsely distributed, they are persistent, and they are multi-dimensional sorted maps. Okay, so you have the different characteristics of HBase, which is an application used to interact with your Hadoop ecosystem. So it's more or less like a component of the Hadoop ecosystem. So you have consistency, sharding, high availability, client API. So, okay, like I said, for consistency, HBase offers strongly consistent read and write. This means you can use it for high-speed requirement as long as you don't need RDBMS supported features, such as full transaction support or typed columns. Then HBase offers transparent automatic splitting, redistribution of its contents. HBase supports LAN and WAN failover and recovery. So just like I said, the client API, for your client API, HBase programming language is Java, meaning you communicate with it using using Java APIs. That's for HBase. Then for your Hive, so now we are talking about mining big data with Hive for querying big data, for querying big databases. So let me say HBase and Hive are almost similar, just that for HBase you use majorly and you access HBase offers programmatic access through Java APIs, but for Hive you use your normal SQL or your SQLite implementations for it. So what's Hive? Hive is a batch-oriented data warehousing layer built on the core elements of. So this Hive is also another application that you use in interacting in your Hadoop ecosystem. So it was built based on the core elements of HDFS and your MapReduce. It provides users who know SQL with a simple SQL implementation called HiveQL. So the SQL implementation of the Hive is your HiveQL. You can use three mechanisms for data organizations like that: tables, partitions, buckets, and on. So one thing you need to know is for your HBase tables are not like your RDBMS tables, because your HBase tables contain timestamp, which is basically being used for versioning. But for your Hive tables are the same as your RDBMS tables because they consist of just columns and rows. They don't contain timestamps attached to every data entry or data information in those tables. Then for partitioning, so HBase, a Hive table can support one or more partitions. These partitions are mapped to subdirectories in the underlying file system and represent different distribution of data throughout the table. So what it means is you can have different partitions of tables in your Hive table, in your Hive, yeah. You can have different partitions. Then you can also have buckets. What they mean by buckets is separating your data into different segments. Let's say, just like now, if you are doing a frequency distribution now, you say from 0 to 10 years old, 10 to 20 years old, 20 to 30 years old. So it's just like you are bucketizing your data. So two things you need to take note here, or the three things you need to take note of here is your HBase tables are not the same as your RDBMS tables. But for your Hive tables are the same as your RDBMS tables because they contain basically rows and columns. Then for your Hive, you can partition your tables. And for Hive also, you can also have different buckets of your data, meaning you can bucketize your data. You can separate your data into different segments. Okay, so for now, let's check which of the following components of Hadoop provides SQL-like access to structured data and sophisticated big data analysis with MapReduce. Okay, that's that. Okay. So which one provides Java access? Yeah, let me just ask someone that. Which of the following Hadoop components provides Java access? Okay, Sunday, I have a question. Okay. Yeah, you guys should come with your questions. I'll
I just want to answer the question you asked.
Okay, yeah, answer.
Is it age-based?
Yeah, so it's age-based that provides you access using Java APIs, yeah. Okay, your hand is still up.
Yeah, I couldn't find I don't know, after putting up the hand, I couldn't find the button to put it down. So I don't know, it just stuck that way.
Okay, thank you.
Yeah, all right.
Okay, so in the next set of presentation, we'll be looking at other tools used to interact with.
So someone is asking a question in the chat.
Okay, so Aditoro, what versioning is? Okay, let me explain versioning in more or less like a simple term for you. So okay, we both go to the ATM machine now. Yeah, you made a transaction. Let's say you withdrew a sum of 10,000 naira from your account from the ATM. Automatically, the ATM sends that transaction detail is being sent to your bank, and that's being saved in the transactions table. Let's say they run a Finacle application in your bank now. Let's say it's being saved in the Finacle table. It's saved. So as at the time you made the transaction, let's say you made the transaction as at 9:30 now. Okay, as you made the transaction as at 9:30. At that same 9:30, that was the entry date and the posted date in which the details of your transaction entered the transaction table at the bank, which is the Finacle table. Then I go to the bank as at 10 o'clock in 10 o'clock that same morning. Let's say I withdraw the sum of, let's say, 7,000 naira now. So my own transaction is entering the bank as at 10 o'clock. So it's being reported and posted in the Finacle table as at 10 o'clock. Do you know that if it comes to versioning now, versioning means I can say, okay, get me the entries I have between a certain time. So as at 9:30, the information about my own transaction has not been recorded yet. It was just, it's most likely the transaction you did last that was recorded as the last entry as at 9:30. So what versioning means is that being able to retrieve information at a particular time, like creating different versions of it. So you can also see versioning in also another different ways apart from using timestamp. So meaning the version you have as at 8 o'clock is different from the version you have as at 9 o'clock. So you can see versioning as also another different way now. So just like your Hadoop ecosystem now, for your Hadoop now, you have Hadoop version 1. When version 1 came out, there were a lot of issues, like you couldn't do batch processes, MapReduce was not there. There was a lot of occurrence of single points of failure because there was no replica and cloning of your different name nodes on your different data blocks. So when version 2 came out now, we had MapReduce, we had a lot of other softwares and applications we could use to interact with the Hadoop ecosystem. So that's also another form of versioning. So you can see versioning as a form of hierarchy that you use to differentiate between different entities of data, meaning different states of an application. So yeah, that's just what versioning means. But okay, let me also try to use a more simpler term to explain versioning again. So versioning is something that you can just explain in so many different ways. So let's say, yeah, just like your water now, water has the liquid form, so you can call that a certain version, you can call that version 1. Then water in a solid state also, you can call it, which is ice block, you can call it version 2. Then water in its gaseous state, which is vapor, you can call it version 3. So that's more or less like version, like being able to call up information at different states or different entities. That's what basically versioning is. But the most common software process of versioning that we use in the IT world these days refers to versioning when it comes to GitHub processes and cloning like that. Yeah. But in data science, in big data engineering and analytics, versioning can mean different things. It depends on what you're referring to. Okay. Wow, we're far behind schedule. So we have other different tools that we use in interacting with the Hadoop ecosystem. So one thing I need you guys to know is that, like I told you, okay, I want you guys to slide. Like I told you, the three major components of your Hadoop ecosystem is your HDFS, your MapReduce, your YARN. But these others, they were created based on one or two of these three. Yet we still refer to them as components because they are part of the community. So meaning there are even maybe newer technologies that we have not even taken into account yet that is actually regarded as a component of the Hadoop ecosystem. But for the purpose of the DASCA certification, this is what they consider the components of to be as components of your Hadoop ecosystem. So like I said, you have the three major ones: HDFS, MapReduce, and YARN. Your HBase and Hive, they were applications created based on either based on HDFS and MapReduce and YARN, or just HDFS and MapReduce. While from Pig, Scoop, Zookeeper, Flume, and Uzi downward, they are mainly Hadoop ecosystem applications you use in interacting with the Hadoop ecosystem. So yet we still refer to them as components of the Hadoop ecosystem. Okay, I'm going to take it back. So you can see from here, tools for interacting with Hadoop. You have Pig and Pig Latin. You have Scoop. You have Zookeeper. You have Flume. You have Uzi. I already told us how Scoop was formed. So let me talk about Pig. I will still talk about Scoop. So Pig was designed to make Hadoop more approachable and usable by non-developers. I can remember I said this when I was explaining the first slide that for those people that don't actually really like coding so much, there are tools they've provided that they can use to interact with the Hadoop ecosystem. So Pig is an interactive script-based execution environment supporting Pig Latin. So it's also a language used to express data flows and the rest, just like your flow process, your flow diagram and the rest. So Pig Latin language supports the loading and processing of input data with a series of operational programs. Okay, so the Pig environment has two modes as shown in the following table. So it has two major modes. So for your Pig environment, you have the local mode and you have the Hadoop mode. Okay, someone is asking a question. Oh, person's trying to get into the call. Okay, so Richard is with us now. So your Pig execution environment, you have the local environment, you have the Hadoop environment. So while we are going through some of all these slides on your own, one way to watch out for things that are very important is those ones that are highlighted in, let's say, light green or gray like this. You need to take note of them because they are more or less likely questions to come out in your certification exam. So for in the local mode, all scripts are run on a single machine. Hadoop MapReduce and your HDFS are not required for all the processes. So he's saying all the processes you require to run using Pig in the local environment, which is on your single machine. You don't need Hadoop MapReduce and your HDFS to run it. Then you also have the Hadoop environment, also called map reduce mode. All scripts are run on a given Hadoop cluster. So you know what makes up an Hadoop cluster? You have your commodity servers or your data block servers. Inside those servers, you have your name node, you have your data node. Then what else you have to take note about pig? Pig programs can be run in 3 different ways, all of them compatible with local and Hadoop mode. These modes are shown in the following table. Okay, that will be our next slide. Okay, so the table wasn't shown. Okay, either ways, I'm going to tell us the 3 different modes the 3 different ways we can run our pig programs. So we can run our pig programs in 3 different ways. The very first way is you can run it as a script. So what does it mean by running it as a script? Meaning you can either edit a text file, then save it as .pig. So what this means is is simply a file containing pig Latin commands, which is your pig language. It's a file containing pig Latin command. Then how do you identify such type of files? So those files are saved, let's say as loaddata.pig. Just like now, a CSV file will be saved as loaddata.csv. But for a pig script, it will be saved as loaddata.pig. Just like your SQL script now will be saved as let's say loaddata.sql, just like that. That's the very first way you can run your pig program, running them as scripts, which comes in form of pig files. Or you can either run them as grunts. So what do I mean by grunt? So a grunt is a command interpreter. A grunt is a command interpreter. In that command interpreter, you can type your pig Latin statement, which is your pig language, on the grunt command line, and the grunt will execute the command on your behalf. So one way, the major reason why people tend to use grunt is because of maybe you want to create pig Latin script based that makes use of if else statements, what if statements, different case statements, and the rest, your logic statements. So you want to run all those type of scripts. So it's advisable to use the grunt command line to run your pig Latin scripts. Or you can either run it, you can run your pig program as an embedded. What that means is that, meaning you can run your pig program as an added extension to your Java program. So meaning you embed it into your Java program and you compile everything together. So it means a pig programs are being executed as part of the Java program using your HBase. So those are the 3 major ways you can run your pig program. You can run your pig program as a script. As a script means you run your normal .pig files. You can either run it as a grunt. What do I mean by that? Meaning you run your pig Latin script statements inside the grunt command line. You can either run it as an embedded. What do I mean by as an embedded? Meaning you run it as an added extension in your Java program. I hope we all get that. If you don't understand it, I can still go over it again. So this basically talks about the different operations supported by the pig programming language, which is pig Latin. So they're calling it pig, and in essence, they said it was created for non-developers. I still don't understand. That's one thing that baffles me. That if it was created for non-developers, people that don't really have so much interest in coding, then I believe then it means that the pig Latin language or the syntax is very easy to comprehend. So the different pig operations you have includes you can load and store data, you can stream data, you can filter data, you can group and join data, then you can sort data and combine data, then split data. Okay. Let me know if you can still hear me, because it seems people are leaving. Hello, are you guys here? Can you hear me?
We can hear you. We can hear you.
Yes, we can hear you.
Okay. So I already told us how Scoop was formed. Yeah, I told you you pick the first two letters of SQL, then pick the last three of Hadoop. That's how Scoop was formed. So basically, what Scoop means is um, um, the sound is better now. Okay. So Scoop is also another application we use in interacting with the Hadoop environment, Hadoop ecosystem. So Scoop is a tool that offers the capability to extract data from non-Hadoop data stores, then transform them into a form usable by Hadoop, and then load the data into HDFS. This process is called ETL, yeah, extract, transform, and load. So what this basically means is that you are carrying data that doesn't belong to that doesn't have the nature of the Hadoop ecosystem. Then you are extracting that data, transforming it, then loading it into the HDFS, which is the Hadoop ecosystem files distribution system. Scoop provides several useful features for interacting with the Hadoop system. The features of Scoop are you can do bulk import on Scoop, you can do direct input on Scoop, so you can import and map SQL databases directly into Hive and HBase. So meaning you can run your HBase and Hive together, all thanks to Scoop. Then you can do data interaction, data export, on and on like that. Okay. Then you also have Zookeeper. So what does Zookeeper do? So Zookeeper too is more or less like, so one thing I noticed about this open source project called Hadoop is that when they seem to be having a major problem in any organization, what they do is they bring their set of software engineers together, then try to create a solution for it. Then publish it out. Since it's open source, everyone have access to it. So that's what open source means. Open source project refers to those projects that anybody can contribute to make it better for people to be able to use. So imagine those things that your yarn used to do. Remember I told you that your yarn is more or less like an administrator. So what they did was some of those things that yarn was doing, they were still having some little issues with some things. That was where Zookeeper, and that was what led to the development of Zookeeper. So what does Zookeeper does? Zookeeper coordinates all the elements of the distributed applications. So you can see we thought the major administrator was Yan, which is the software layer. Now we also have Zookeeper also for more advanced operations, meaning places where your Yan will not be able to perform well. The Zookeeper comes in for it. So the Zookeeper coordinates all the elements of your distributed applications, meaning any application you have on your Hadoop ecosystem, the Zookeeper coordinates every single element of it. So some useful features of a Zookeeper include process synchronization, configuration management, self-election, and all. Just like I said, always take note of the statements highlighted in light green. So you can see for configuration management, which is majorly the reason why I feel Zookeeper was developed. Zookeeper can be used to send configuration attributes to any or all nodes in the cluster when processing is dependent on particular resources being available on all nodes. Zookeeper ensures the consistency of the configuration. So it's more or less like, remember that normally what should be doing this thing, that this configuration management that Zookeeper is doing is actually our yarn. It's actually the resource manager in our yarn. But it's like there's some loopholes in the whole ecosystem thing, and they notice that to reach out to some standby resources or some replica nodes that were created, or some standby nodes that were created, you can only access them using maybe a customizable configuration manager using Zookeeper. So that's why they built Zookeeper. So what Zookeeper will do is, if a process depends on some particular type of resources, Zookeeper will try to make sure that that resource to run that process is available for that process for it to run. Then another thing Zookeeper does is self-election. Zookeeper understands the makeup of the cluster, of the Hadoop cluster, and it can assign a leader role to one of the nodes, meaning either of the nodes or to one of the nodes. This leader or master handles all client requests on behalf of the cluster. Should the leader node fail, another leader will be elected from the remaining nodes. So what Zookeeper does here is that if the major leader name node fails, if that one should fail, because there is Zookeeper present in the environment, an election will be done immediately. It would elect another node that is a total replica of the failed leader node before. It would elect that node as the new leader node. Then you also have Flume. Flume is also another application used in interacting with the Hadoop ecosystem environment. So what does Flume do? So Flume is a distributed, reliable, and available system for efficiently collecting, aggregating, and moving large amounts of log data from many different sources to a centralized data store. So what Flume does is that it's as if it is carrying the metadata stored in different sources to a centralized place for you. That's what Flume does. It carries data of maybe your web log, your transactional log. It carries your data of, let's say, metadata of your different data nodes, of your different name nodes, of information of different processes running in your Hadoop cluster. It carries everything to a centralized data store. So that's what your Flume does. So Flume is very popular for moving large quantity of data, of streaming data into your HDFS. That's also another thing people use it for. A lot of people use it for moving all those real-time large data, most especially streaming data, all those data that is extremely large. Like you can imagine the number of people querying Google at this particular time now. So let's say someone has access to an API now and decides to get the BigQuery information, all the logs of those BigQueries, then load it into an HDFS. The person will be needing Flume to do that. So you can use Flume to transfer massive amount of data. Just like I said, a very common case of using Flume is collecting big data from one system, let's say a bank of web servers, and aggregating it into your HDFS for further analysis. Okay. Then you have your Uzi also. Your Uzi is also another application used in interacting with your Hadoop ecosystem. So like I said, it is an open source workflow and coordination service to manage data processing jobs for Apache Hadoop. It is an extensible scalable data web service. So all these applications, basically, you just need them to do different things. So this one is also performing coordination of workflow and the rest also. So the major thing is Uzi is a coordination engine. So it runs all your workflow jobs, all your scheduled jobs based on predefined schedules and data availability. So basically, it's more or less like, how do I put it? I'm looking for a very simple name to give it. Uzi is more or less like the supervisor that coordinates everything. Okay, that says, okay, run this job now. In terms of workflow, this should come first, this should come first. This one depends on this. It's just like now, someone who wants to brush his teeth in the morning now, the person needs to do what? The person needs to get his toothpaste, open it. So definitely, if you cannot open your toothpaste, you can't get some paste into your toothbrush. So definitely that workflow means you must open your toothpaste before you can be able to, ideally you should open your toothpaste before you can be able to brush your teeth. So what Uzi does is that the whole workflow coordination, it makes sure that anything that depends on another thing to run, it is available, most especially when it comes to data that is needed for a particular task or operation. So Uzi 2 has also been designed to scale and can manage a number of workflows in a Hadoop cluster. Okay, so one thing to note, Uzi runs as a service in the cluster, and clients submit workflow definitions for immediate or later execution. So Uzi is more or less like a service running as a job scheduler in your Hadoop cluster. Okay. Okay, this just says more things about Uzi. Then knowledge check. How does scoop work? What are some of the capabilities of Zookeeper? Then important points for us to remember. So, okay, does anyone want to answer how does scoop work? First of all, tell me how is scoop formed? How was the name scoop formed? Then another person should tell me how Zookeeper works. Okay, Sunday, you can go on. I thought Sunday was raising up his hand. You can go on.
I said Scoop is actually formed from the formation of both SQL and Hadoop.
Okay, so how does it work? Do you know how scoop works?
Yes.
Okay, go on.
Okay, the major function of Scoop is just for ETL processes. That's for extracting, transforming, and loading of data.
Okay, so what kind of data does it work on, basically? Okay, let me help you. It transforms and works on data that is in non-Hadoop format. It transforms those data, so you can be able to load it into your HDFS, which is the meaning it transforms those non-Hadoop format data. Yeah, data. It transforms it, then helps you load it into your HDFS. Meaning as if you are transforming data from non-Hadoop form to an Hadoop format, so you can store in your HDFS. It is a major ETL, just like you said. You added to, do you want to say anything? Okay, so who wants to tell me something about Zookeeper then? I can remember I said Zookeeper is just like Yan. So who wants to tell me something about Zookeeper? How does it work? Should I call names? How does Zookeeper work? Okay, Henry, are you with us? Hello, Henry.
Yes, I'm with you, but I'm sorry, my network has been messing up. I've been coming and going and coming and going. Sorry,
Okay.
please, I can't answer that.
No problem. So you can help us. Toby. Is Toby not on this call, or are some people just on this call just like that and not Ubet, Toby, people that haven't heard their voice today? Ubet, Toby, Tammy. Can you help? Yeah, Zookeeper. Okay, I'll go over it again. So Zookeeper is more or less the Hadoop way of coordinating all the elements of these distributed applications. So meaning, remember I told you I compared the Zookeeper to your Yarn. The same thing that your Yarn does for the Hadoop cluster, which uses the resource manager to administrate over your data node, your name node, and all. So the Zookeeper is like it administrates over your HDFS, your MapReduce, your HPs, your Uzi, your Flume, your Scoop. So it's more or less like the coordinating factor that coordinates the processes of all these applications. So let me give you an example now. So let's say you want to set up a large-scale distributed system that requires different services now. And these services should be able to discover each other. For example, now let's say you have a web service that might need to locate a kicking service to process a query. So the web service needs to locate a kicking service to process a query. So Zookeeper makes it possible that, okay, normally you'll be like, it is not mandatory for this to have a fixed IP address, but Zookeeper makes it possible that these things are able to communicate with each other for that query to be able to run. So that's what Zookeeper does. It coordinates the processes of the different applications. Let's say your Scoop, your Hive, your HPs. So it coordinates the different elements of your Hadoop ecosystem. Please let me know if you have any questions before we end or round off today's class.
I have a question, sir.
Okay, go on.
I want to I just need clarification on this. Looking at the fact that, okay, fine, I understand that yeah, HDFS, YAN, and MapReduce are the major component of the Hadoop ecosystem. Fine, but I want to know: is it that these components can they be used interchangeably? Like, is it that if I don't want to use HDFS, I can use YAN, I can use MapReduce? That's just what I want to know. Or they have different functions entirely.
Okay, so okay, so if I get a question right, yeah, like, can you use them independently, like without each other? Definitely, if you are, I don't think it's possible, because if you are going to making use of tools of the Hadoop ecosystem to handle your big data, one way or the other, if you are making use of HDFS, you would make use of MapReduce. So those three major ones, they are like, there's no how you wouldn't, or even though you don't make use of them, so you make use of a tool that you make use of a tool that was built on the combination of one of two or three of them. So that's just how it is. So they work hand in hand. That's why I refer to them as the major component, like they're the major things you should add, they're the major components of your Hadoop ecosystem.
All right, thank you, sir.
Okay, any other question?
Yes, I have a question, please.
Okay, please go on.
Okay, thank you very much for all you've said so far. But I think I'm kind of finding it difficult to understand this Hadoop of a guy. As in, I don't understand. So my question is, this Hadoop, is it like how do I put it now? Is it like an application software? Is it like a cloud something, or is it like, I don't know. Please just help me understand that. Then along the line, you made mention when you were talking about the components. There was a point that you mentioned that Yarn is the software, like the software platform or something like that of the components of the ecosystem. So invariably, are you trying to say that the AGFS and the what's the other one? Second one, the AGFS and the I forgot it. And the second one you mentioned, are they hardware? Are they hardware components? I don't know. Please just help me. Then, thirdly, trying to put these things in perspective of okay, let's say real life application. The what do you call it? The other components you mentioned, HPs, which is used for interacting with the Hadoop ecosystem, the Hive, the Scoop, and all that. are they like also application software that you can download, or I just need to understand that. My question is just around that, everything I've mentioned like that, because it's kind of seeming cloudy to me. Thank you.
Okay. So thank you very much for your question. So the very first thing, like I told you, so the very first question you asked is, okay, does it mean that HDFS and MapReduce are totally hardware applications, are totally
Yeah,
hardware devices? No.
yeah, something
Okay.
like
So
that. Okay,
I wouldn't necessarily say yes, they are
okay,
hardware devices. No, they are not. So we are more or less like making it to conceptualize it like hardware. Normally, if you have a server or a data center, okay, most times actually, as a big data engineer or as a big data analyst, you will not even be relating with the hardware tools. Yeah,
okay,
most like it's the IT guys or the data center administrators or the system administrators that will be interacting with these tools. So what I meant is that when I said YAN is the software layer, so YAN is more or less like an application that was built as a load balancer for the HDFS and the MapReduce to work well. Yeah,
okay.
to administrate over the activities of the HDFS and the MapReduce. Then your Hadoop is a platform. Yes, like you guys already did your lab now. You already
No,
did
yeah,
your lab now.
okay. Uh, so I'm sorry to cut you short. Now, the is it like because the lab, I don't know, we don't really have access to it. Maybe that's why everything is seeming kind of, cloudy and all that. So is it like if we have that VMware sort of that the lab? So is it that we are going to be having all those platforms in it, whereby we can?
Yeah, exactly. So your VMware is like your virtual. So let me put it this way now. So your VMware is like your virtual computer. So for some processes or for some of the labs you will be doing with your VMware, you would need internet access. So the Hadoop and the other applications, your Hive, your HBase, your MapReduce and the rest that you run using your VMware. So for those ones that don't need the internet connection, you already have them pre-installed on your VMware. So normally normally for those ones that normally this is how it is. Normally your VMware which is a virtual computer on your PC, it should have its hardware components located somewhere. Like, I'm trying to give you a real life scenario because this Aska is more or less like a controlled lab environment. So it will have its own hardware component, more or less like you are doing cloud computing now. So let's say, yeah, just like now, people that have done machine learning using Google Colab now. For those of you that have done machine learning using Google Colab now, um, you ask for GPU enablement. You ask for Tesla P200 GPU. So you have access to P200 GPU on Google Colab. Ideally, the GPU is not running on your system, but you have access to it because you are connected on your Google Colab. You are connected to a virtual machine in a Google data center, and that Google data center has maybe different Hadoop clusters, different other types of data clusters used for handling big data. So it's more or less like you are relating with it. So for your VMware, it's more or less like a control app you've already installed in your computer. That's why if you notice it is quite large, it's quite heavy. So that's just how it is. They are basically software applications, but for some of them, you can actually point to their hardware somewhere else, not necessarily within your environment, somewhere else.
Okay. 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 So I might want to ask. that can you hear me, please?
Yeah, I can hear you.
Okay. So take for instance, if we are to how do I put this now? If let's take for instance a real life, maybe I'm working on a project sort of, and I need um to I don't know so are you saying that in a real life there's always a hardware component to all these things, because the VMware has already taken out that part, you understand? But what you're saying now is that in a real life setting there's always a hardware part of this Hadoop. Is that what you're saying?
No, not necessarily. Not necessarily, marvelous. Not necessarily. So, like now, I can have. So it is not necessary. I can give you access to a certain Hadoop system or just install it. So, how would I put it now? There's not always a hardware component that you can point out to. Sometimes you will be unaware, or most times you will be unaware of it. You just need to install the software, then have
Okay.
your necessary credentials, then carry out your operation.
Okay.
So it's like, how do I put it? It's like the person is like the person querying a certain, let's say I'm querying a certain database called transaction database now on the server now. I necessarily don't know where the server is, but every time I connect to a particular Wi-Fi network, I'm able to connect to the database through my client application. Do you get? Through my client application, but you don't even know if maybe the database exists somewhere or not.
Okay. Well, thank you so much. I believe as we probably when we have
Yes. So the thing
the
is, as we move forward, all these things like it would unfold more. You get to understand it better. You get to understand. Okay, so I don't know. Let me find out. The last lab you guys did was what? Or it's all just explained.
Just
I don't know. Is the
introduction
man
to the lab.
just
It was
introduction
the
to
lab. It
the
was
lab?
today actually. It was today.
Oh, this morning. Okay. So that means I'm coming. Let me start chemistry. So, wow, I'm coming. So that means we'll be doing framework for processing on Hadoop together on Wednesday morning. That's map reduce and yarn fundamentals.
Sorry, I want to understand you. This particular aspect, is it for engineering or for analyst?
So it is both for engineering and analyst.
Okay, thank you.
Yeah. So I don't know. I would reach out to Emmanuel. I don't know how you guys because I know right from the very first module. Yeah, let me check. Let me confirm. Right from business applications of big data. Okay, yes, you guys have done the two major labs. So this particular understanding Hadoop ecosystem, it has its own lab too. Then the one we do on Wednesday also has its own lab, which is, I guess, the final thing for both analyst and engineering, after which you guys will split up. Okay, so thank you very much, everyone. We'll see you on Wednesday morning.
thank you, sir, for your time.
What is left now? I should leave as well.